Hello everyone, welcome to A plus BI. This channel is all about complex numbers, and in this video we're going to be simplifying a trigonometric expression with complex numbers. We have 1 plus cosine 2 pi over 5 plus I times sine 2 pi over 5 all over cosine of pi over 5 plus I sine pi over 5. And we're going to try to simplify this expression, write it in the simplest form possible. And you might be questioning, like, what does this problem have to do with complex numbers? You're gonna find out in a little bit. So I'll be presenting two methods and you're gonna get to decide which method is better or which one you like better. All right, so let's get started. First method. For my first method, I want to use some identities which are known as double angle. Some people call them half angle, but I think double angle is more appropriate. And this is how it goes. For example, cosine of 2 alpha can be written as three different ways. The original one being cosine squared minus sine squared, and then we use the Pythagorean identity, so on and so forth. The one we're going to use is going to look like this. Cosine 2 alpha can be written as 2 cosine squared alpha minus 1. And the reason why I go with this one is I want the 1 to cancel out. I do have a positive 1 here, notice that. And if I can use a formula that has a negative 1 in it, then I can get rid of the 1's and end up with something just trigonometric. Make sense? That's the whole idea. What would happen if you had 1 minus cosine? Then you would use a different formula. So your goal is to always get rid of the 1's. Make sense? I hope it does. Now, let's go ahead, and since 2 pi over 5 is 2 times pi over 5, you knew that, right? We can go ahead and write the 1 plus cosine 2 pi over 5 as 1 plus 2 cosine squared pi over 5 minus 1, and the 1's cancel, and we end up with 2 cosine squared pi over 5. So this is going to be 2 cosine squared pi over 5, right? Let's go ahead and do that. And we're going to get 2 cosine squared pi over 5. And then plus I sine 2 pi over 5. Now we also need to do something for 2 pi over 5. So let's go ahead and do this. Let me do both and then we'll do the replacements. We can also use a double angle formula for sine 2 alpha, but that's actually easier because there's only one formula, which is nice. Sine 2 alpha can be written as 2 sine alpha cosine alpha. So sine of 2 pi over 5 can be written as 2 sine pi over 5. In this case, alpha is pi over 5 multiplied by cosine of pi over 5. Let's go ahead and make both of these replacements in our expression. We have 1 plus cosine 2 pi over 5, which is going to be replaced with 2 cosine squared pi over 5 plus I times 2 sine pi over 5 times cosine pi over 5, which is going to replace sine 2 pi over 5, 2 sine, which is this one, pi over 5 cosine of pi over 5. All over. And in the denominator, we just have cosine pi over 5 plus I sine pi over 5. Let's not do anything about these two because we already got everything in terms of pi over 5, so it's all good to go. Now let's go ahead and simplify this a little bit, like by factoring. We have a 2 in common and also cosine pi over 5. If we take that out, we get cosine pi over 5 plus I times sine pi over 5 divided by cosine pi over 5 plus I sine pi over 5. And this is just awesome, don't you think? These two expressions cancel out and we end up with 2 cosine pi over 5. So that should be the answer in the simplest form, right? But what is cosine pi over 5? If you knew the value of cosine pi over 5, then you could easily plug it in. Let's think about it. In degrees, that would be 36 degrees. Does that trigger any memories? If you've seen this before, there's actually an interesting golden triangle that you can use, which is the 72, 72, 36 triangle. And actually, if you make a picture like this, you're going to realize that, okay, we get quite a few isosceles triangles. This is also isosceles, that's isosceles. And we have the similarity of 3 triangles. And if you make some, naming like sides, like you can call this x, you can call this 1, and you can kind of go about using the law of sines, and then the, some double angle formula, so on and so forth. And eventually you're going to arrive at cosine of 36, which I believe something like this. Root 5 plus 1 over 4, I think, right? Something like that. If I'm not mistaken, it should look like this. And then you can just plug it in, double it, and you're going to get root 5 plus 1 over 2. So you're going to get a numerical answer anyways, but I'm going to show you a couple different versions of this. But before that, we need to do the second method. And you know why? Because I think the second method is awesome, but I could be biased. You're going to get to decide which method is better. And there's actually a third way to do it, which I should briefly talk about. But if you know of any other methods, please let us know in the comment section down below. Do not hide it from us, okay? So here's the original expression, 1 plus cosine 2 pi over 5 plus I sine 2 pi over 5 over cosine of pi over 5 plus I sine pi over 5. Again, you could be questioning like, why does this problem appear on this channel? Isn't this like a trigonometry problem where you use double angle formulas? Yes and no. The reason why this appears on aplusbi, by the way, that's the name of this channel in case you didn't know. And I have another channel called Cyber Math where I do algebra, number theory, and trigonometry problems, including this one. But this is more appropriate. And now let me tell you why. We're going to use another method, and this will completely use complex numbers. By the way, if you're new to complex numbers, go ahead and check out my lecture videos that'll show you the basics of complex numbers. And if you have any questions, feel free to ask. So let's take a look at this expression first. I'm going to call this z. I'm not going to go into the details because you should know this. If not, again, refer to the lecture notes. But here, if you call this z, the Moivre's theorem, I could never say the French pronunciation. That's why I kind of go with the American English version. But it's, I think, spelled like this, something like that. I could be wrong with the punctuation marks or whatever. But this theorem basically tells us that you can easily take a number z like this and raise it to any power. In the case of you're doing it second power, all you have to do is double the angle and square the modulus. But in this case, the modulus or the absolute value is 1, so you don't need to worry about it. You just have to double the argument. You get that? So if this is z, this is z squared. You got that? Awesome. I really wasn't thinking about this method, but then it just occurred to me, wow, this looks really cool. So our expression turns into the following: 1 plus z squared divided by z. And guess what? I can write it as z plus 1 over z. What is z? Z is cosine pi over 5 plus I sine pi over 5. Here's the thing. If you have a complex number written like this, its reciprocal is also going to be its conjugate because absolute value of z is 1. Therefore, you can just write it as the conjugate, I shouldn't say conjugate, the complex conjugate of z, which is cosine pi over 5 minus I sine pi over 5. And guess what? The minus I sine pi over 5 cancels out, and we end up with the same thing. Surprise, 2 cosine pi over 5 would be the answer. And what is the simplest form? I guess you could leave it like that and evaluate it if needed. The third method that I was thinking about could be if you know the values of sine and cosine of 2 pi over 5 and pi over 5, you could directly plug them in. That's probably what Wolfram Alpha did, because if you look at the solutions, ta-da-da-da, this is the, are you serious? Is this the exact result? Can you not simplify this? Come on, Wolfram Alpha, you can definitely do better than this, or maybe this one. Does that look familiar? Right? Anyways, this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.